All right, so today we're going to be learning about systems of inequalities. Similar to systems of equations, we're working with two or more linear inequalities that are graphed together. The solution to a system of inequalities is the overlapping region of points that satisfies both inequalities. So like when we're working with system of equations, we would have two lines, maybe a line that looks like this and a line that looks like this. And the solution would be this point right here where they intersect. When we're dealing with inequalities, if you remember when we were just graphing single inequalities, inequalities can be dotted or solid lines and they have shading. And so, for example, if this was the solution to the first inequality and this is the solution to the second inequality, we're not just anymore looking for an overlapping of a one point, but the area where they overlap. So in this situation, this area down here would be the solution. So we're going to see that as we work through some examples. So the steps for solving a system of inequalities are that we have to graph to see this because there's a large area of points that will be included in the solution. So we're not going to solve by substitution or elimination. We have to graph it to be able to see that area. So in order to graph, each equation needs to be in slope-intercept form, which, as a reminder, slope-intercept form is y equals mx plus b. The reason that slope-intercept form is important for graphing is because we need to be able to identify what our slope is, m, and what our intercept is, b, so that we can graph it. Once we have our slope and our intercept identified, we're going to graph the inequality, and we want to keep these things in mind. We're going to identify the slope and the y-intercept, which I just identified, m and b. Slope is m, y-intercept is b. We want to determine if the line is dotted or solid. So remember, with inequalities, we don't have an equal sign anymore, but we could have a greater than or less than sign. If it's greater than or less than, then the line is going to be dotted. However, if it is greater than or equal to, or less than or equal to, the line will actually be solid. So we need to pay attention to that. And then once we have our line graphed, we need to decide if we're going to be shading above or below the line. And finally, once we have both inequalities graphed, we're going to look for the solution. It's the part where the graphs are going to overlap, and we're going to mark it with an S, okay? So we'll be able to see some examples of this down here. So we're going to solve this system of inequalities by graphing. So the good news about number one is that both equations are already in slope-intercept form, so I can very easily identify m and b. So a suggestion I have is just to work entirely with one inequality at a time. So in other words, I'm not going to try and find m and b of the first one and then find m and b on the second one and then go back to the first one and try and graph it and then the second one and then finally do all the shading. I think it's best just to do everything for the first equation and then everything for the second equation. So I'm going to model that. So if I'm looking y equals mx plus b, my slope is 1 and my intercept is 2. So I'm just going to write that out so I have it down. M equals 1, b equals 2. So that means b is my starting point. I'm going to start at 2 on the y-axis, which is right here. And for a slope of 1, that's positive, I'm going to go up 1 over 1. So this is up 1 over 1. So up 1 over 1, up 1 over 1, up 1 over 1, and then down 1 over 1. I can continue the pattern this way. Now, before I draw my line, I want to check, is this line going to be dotted or solid? So I have to look at the symbol. Well, this is y is greater than, there's no equal to, so it's actually going to be a dotted line. Okay, and also I need to add shading. So if y is greater than this line, I want to look for the values of y that are increasing. So y up here is getting more positive. This is positive. And down here, the downward arrow, y is actually getting more negative. So if y needs to be greater, I'm going to shade up. And my shading, I'm going to draw just kind of like lines like this, and there's a reason for that. You'll see in a minute when we have our second one graphed, it gets a little messy, and we want to be able to clearly see our solution. So I'm going to move on to the second one. Once again, it's already in slope-intercept, so I can easily identify my slope and my intercept. So m is -2 and b is -1. So I'm going to start on -1, which is down here. For a slope of -2, I'm going to go down 2 over 1. It's negative, so I have to go down and over. And it should be going downward like this, and then up 2 over 1, up 2 over 1. And before I fill in my line, I want to check it is less than or equal to, so this will be a solid line. Okay, now that I have my line, I can shade. In this case, y is less than or equal to. So if this is positive y, this is negative, y is less than is going to be below this graph. And I'm going to shade sideways so that it's actually really clear to see what my solution area is. I'm looking for the area where both graphs are overlapping, which is this area over here. It goes from here, it's dotted along this line, and then it's all in here is my solution. So I'm going to mark that with an S. And just to clarify some things, if we were checking points, clearly anything over here is not a solution. And with the system, anything in this area is not a solution because it's only the solution to one of the inequalities. Same with things up here, not a solution to the system. Anything in this area is a solution because it's covered by both. And then we want to check the lines. Since this is a solid line, anything on this line is a solution. However, anything on this line is not a solution because of the dotted line. So if I ever asked you to check points, you would need to know those things exactly, what is a solution and what is not. But in general, anything in this yellow area will be a solution. All right, so we're going to move over to number 2. In this one, we do not have our equation or inequalities in slope-intercept form, so I'm going to go ahead and move this x by subtracting it from both sides. X minus x cancels, leaving me with y is greater than -x plus 4. Now I can identify m and b. M is -1 and b is 4. Meaning I'm going to start on 4. 1, 2, 3, 4. And for a slope of -1, I'm going to go down 1 over 1. Down 1 over 1, like this. And now when I check my equation, I want to look at this one. Y is greater than. There's no equal to, so this will actually be a dotted line. And my shading, since y is greater, will go up. All right, looking at the second equation, I also need to get the y by itself, so I'm going to subtract x. I'm left with y is less than -x minus 1. So m is -1 and b is also -1. So this is my starting point. My slope is down 1 over 1, like this. And at this point, you should be able to tell these lines are not going to intersect. They're actually parallel. Once again, I have less than, so this is going to be a dotted line. And if y is less than, I'm going to be going down. So this is a situation where actually there is no solution because there's actually no overlapping area. So my answer here is no solution. Okay, so moving on to applying these systems of inequalities to word problems. Here's a little note. It says, in real-world problems, sometimes only whole numbers make sense for the solution, and often only positive values of x and y make any sense. So you've got to think about what your situation is. Like if we're talking about time, that's what it's saying. Like if you're solving for time, negative time doesn't make sense. So you need to make sure you get positive values. Same with whole numbers. If we're talking about like how many people, it doesn't make sense to have 3.2 people. Only whole numbers make sense. So we want to just keep that in mind as we're solving these real world problems. So we're going to take a look at number 3. It says, Mr. Flowers is on a restricted diet that allows him to have from 1,600 to 2,000 calories per day. His daily fat intake is restricted to between 45 and 55 grams inclusive. What daily calorie and fat intakes are acceptable? List 3 possible solutions to the problem. Okay, so it looks like Mr. Flowers here has a range. He can have between 1,600 and 2,000 calories per day. So I'm trying to think how we would show this. If we're looking at this graph, 1,600 calories are down here. So 1,600 would be like, this is 1,500, 1,600 would be about there. And he can have between 1,600 and 2,000, which means anything in this zone is okay. Which is kind of a funky situation. So I'm just going to kind of show that this zone of calories is okay. Then we're looking at his daily fat intake. It's restricted to between 45 and 55 grams. So if we're looking at fat, here's 45 and here's 55. So if we kind of just show this section right here, that is how much fat he's allowed to have. So then it says, what daily calorie and fat intakes are acceptable? List 3 possible solutions to the problem. So this was not like a traditional solving a system of inequalities. In this case, I think we're just kind of showing visually on this graph what's acceptable, and then we can see the points where they overlap are right here. This is where both graphs overlap. So if I'm trying to give 3 possible solutions to this problem, he can have any calories above 1,600 to 2,000. So he could have, 1,700 calories. And if we go up to fat grams, if he had 1,700 calories, then he could also have anything between 45 and 55, and 50 grams of fat. So that's one possible solution. A second possible solution would be like 1,800 calories, and he could have 1,800, and he could have exactly 45 grams of fat. And I think you see here, like, really anything in this range, any point. He could have up to 2,000 calories. And that would be his maximum calories, and his maximum fat would be 55 grams of fat. So there are many solutions that would work here. I've just picked 3 points that lie in this space right here, which is all the possible solutions.